So today in this talk, I'll be talking about instabilities in the water wave problem, and I'll try to relate how those instabilities within the context of the full problem and the instabilities that you can or cannot see in their asymptotic models, how those maybe in some cases are related. So this is joint work with a bunch of people: Katie Oliveris, who's now at Seattle University, Ben Siegel, who is now at American Airlines, Olga Trichenko, who is now, I guess I should just say Western instead of Western Ontario, Jeremy Upsall, who's still at Washington, and Ryan Creedon, and then also John Deconinck at Berkeley. I kind of wish that I had maybe another 2 months to, before I had to give this talk, because then a lot of the results that Ryan is working on now would be a lot more exciting to include, but maybe I'll mention a few things. Okay, so I don't need to introduce water waves to this audience. There's been a lot of work on understanding all the kind of different shapes and patterns that we can have in water wave problems. And then, of course, there's very many different asymptotic regimes describing different types of these shapes. What I want to focus on specifically is stability, and I'll give you some results, historical and some not so old ones, for the Euler-Water wave problem stated here. I'm not going to go over this. Basically, this is just the standard Euler-Water wave problem. No viscosity, no vorticity, one-dimensional, although I will say a couple of things about transverse instabilities as well. Okay, so let's talk about history. Really, the beginning of the initial stages of thinking about the instabilities that you could have in the water wave problem go back to 1967 with both Benjamin and Whittam publishing papers where they proved that waves in deep water are unstable with respect to the modulational instability. This is now referred to as the Benjamin-Fehr instability, of course. Rigorous proofs. In 1995, Bridges and Mielke presented a proof. That proof does not work in infinite depth. That was resolved more recently, well, very recently, by Gwynn and Strauss. But this is all about the Benjamin-Fehr instability, about the modulational stability, right? So this is periodic wave trains that undergo modulation, and so what becomes of this modulation and goes on. In the spectral, so if you linearize around your wave and you examine the spectrum of the linear problem that you're dealing with, then the Benjamin-Fehr instability manifests itself by having this cross at the origin. Okay, so this is the spectral plane, and then typically for Benjamin-Fehr you have this cross at the origin. Okay. MacLean in '82, I have to move some of the zoom controls out of the way here. MacLean in '82, in his thesis, and lots of other people, Melville and Zhang and so on, looked at, there were a lot of numerical studies on stability and instability. MacLean especially produces one plot, very much like the one that I have below here. So you can see my mouse move, right? Okay, so we have on the vertical axis, we have the transverse wave number of the perturbation. So basically, when that is 0 on this horizontal axis, we're dealing with one-dimensional waves. Okay, so although there's lots of stuff to see here, lots of instabilities, everything that's not dark blue is an instability for transverse perturbations. You can already see that even for longitudinal perturbations, so when there's no transverse component to the perturbation, that there are instabilities present. But it's fair to say that those have been ignored for quite a bit. This, as I said, this figure right here is not a reproduction of what MacLean had. It's this is a computation by Katie Oliveris. I was in her PhD thesis. And it's basically replicating the results that MacLean found, maybe with a little bit higher resolution. But conclusion from McLean was, if you look at two-dimensional waves, meaning one-dimensional surface, these waves are susceptible to all kinds of instabilities, both transverse ones and longitudinal ones. Okay, and that result is true both in shallow and in deep water. And I'll define deep water in a second a little bit more carefully. Okay, so because of all the attention that the Benjamin Fear instability received in that time period, there was this belief, and you can, for instance, find this in the textbook and in the book by Ablitz and Seeger, that waves in shallow water are stable. Okay, and so then one question is, how do we relate that to the asymptotic models that would describe waves in shallow water, like for instance the KdV equation? Okay. The nonlinear Schrödinger equation is often, can be derived as describing the dynamics of modulated wave streams in deep water. It's one application, one derivation. And so it should not surprise you that by construction, the dynamics of this equation is in perfect agreement with what you get from the Benjamin Fear instability in the full problem. Okay, because that's how we set it up. If you now go transverse, just like what we did for the water wave problem, then there's a little bit more to see. So right here, same as before, what I have, well, no, actually the axes are reversed. On the horizontal axis, I have the transverse wave number. And then on the vertical axis, we have the largest real part of the elements of the spectrum. Right here, going through the origin, is a curve that is very straightforward to obtain, and this was done by Zakharov and Rubinchik. And then anything that goes beyond this, the tangent to this curve, is done by a variety of other people. And I've got about, looks like I have about results from about 4 different papers on here. Okay, and you can see that there's a lot of disagreement in terms of what happens once you get past the Zakharov-Rubinchik regime. In other words, once you get past long transverse instabilities. Based on these works, a lot of which seem to indicate that there was no instability once you got to sufficiently short waves in the transverse direction. Now, there was another prevailing belief, that there was a largest unstable transverse wave number. In other words, there is really a cutoff on this horizontal axis, and then once you go to the right of that cutoff, nothing else happens. And this actually impacted the design of wavelengths in that era. So when people wanted to do one-dimensional wavelength experiments, these tanks were then designed to be so narrow that any of these unstable transverse modes would not fit in the width of the tank. Okay. But it turns out that that's not entirely a correct thing to do, because the correction of this historical figure on the left is this figure on the right, which shows that for all transverse wave numbers, there are unstable modes. The growth rates associated with these instabilities get small, and they're definitely significantly smaller than what you have here in the let's call it the Zakharov-Rubinchik curve. But there are instabilities no matter how short the transverse perturbations get. And that's work that we did in 2006 with Velnowski and Carter. Let's go back to shallow water. So the KdV equation written here should describe long waves in shallow water. How about, what can we say about stability or instability? In '74, Benjamin again, using Arnold's method basically, proved that KdV solitons are orbitally stable. He was able to adapt the same method to the periodic setting, so the total wave solutions, as long as he restricted to coperiodic perturbations. So in other words, perturbations of the same period. So the conclusion there is that these periodic waves are also orbitally stable with respect to these coperiodic perturbations. He, looking at his method of proof, he saw different things fail when he allowed for subharmonic perturbations. These are perturbations of still periodic, but with a period, an integer multiple of the underlying wave. And he conjectured that the KdV nodal waves would not be orbitally stable with respect to subharmonic perturbations. And then there's a little bit of a contentious history. Oh yeah, I should first mention McKean. McKean, relying heavily on integrability, proved that the periodic waves were indeed stable. So it's an alternate proof to what Benjamin did with respect to coperiodic perturbations. I think McKean's proof could be extended to go beyond that result as well, and perhaps say something about subharmonic perturbations. But it's not the route we took. From 2005 to 2010, there were different claims made that Benjamin conjecture about the instability with respect to subharmonic perturbations was true. There was an erroneous proof. The preprints were floating around. This was presented at conferences. I've been at least to 3 talks at conferences where these results were presented, but they were incorrect. And we proved in 2009, 2010 that the periodic solutions of KdV are orbitally stable with respect to all subharmonic perturbations, no matter how large the period. So let's go a little bit back to the full water wave problem. So on the horizontal axis, you basically have the depth of the water. So this is all for a Stokes wave of fixed amplitude, relatively small amplitude. And then on the vertical axis, you have the maximal growth rate that you observe in the spectrum. So if you just look at this dash curve right here, then that is just a confirmation of the Benjamin fear instability happening when the combination KH, the dimensional depth, is greater than 1363, and that has commonly been called, anything where KH is greater than 1.363 is commonly referred to these days as deep water. Anything that's less is commonly referred to as shallow water. So right here, you see the Benjamin fear instability take off exactly at this 1.363. But there is this other curve. And this other curve seems to exist for all values of KH, including in deep water, but also in shallow water. You see that this other curve has growth rates that go up quite steep, quite significantly as you decrease the depth. The reason for that is, as I stated earlier, this plot is for a fixed amplitude solution. And so if you fix your amplitude, but you increase the depth, in effect, you're dealing with a larger and larger amplitude wave, hence these large growth rates that you see. But what is this curve? So let's actually take a look at the spectrum for the Stokes wave and the Euler water wave problem. So on the left, you have 2 different illustrations of the stability spectrum for a Stokes wave in the context of the full Euler water wave problem. This first, in the upper left corner here, this is a stability spectrum for a wave in deep water. And so you have right here, of course, all of these spectra have this 4-fold symmetry that you'd expect for a Hamiltonian system. If I zoom in on this part right here, which seems to have the largest growth rate, then that is nothing but the figure 8 that we come to expect from the Benjamin fear instability. Okay, but you see that there is something else as well. And if I zoom in on this right here, and stretch it out in the vertical direction, you see that you get a bubble or isola of high frequency instabilities. We call them high frequency instabilities because the imaginary part of the eigenvalue is not 0. Okay, that's for deep water. If I go to this bottom left figure, now you're looking at the instability spectrum for a wave in shallow water. So the Benjamin fear instability, here's the origin. Benjamin fear instability is absent here, but you do have something else. If we zoom in on now this in the upper half plane, what has the largest growth rate, that is right here. that corresponds to an isola, just like it did in deep water. And similarly, if we zoom in on the one above it, there's another isola there. You can even see the a much smaller isola above that as well. So in this case, you can see up to 3 of these high frequency instability bubbles. Now, I want to link that with what I just said about the KdV problem. I told you that in the KdV problem, colloidal waves were orbitally stable with respect to subharmonic perturbations of arbitrary period. How does that mesh with what we have here? Well, the fact is that the KdV equation, of course, occurs in a long wave regime, and the perturbations that are the cause for the instabilities that we see here in shallow water are not captured by the KdV regime. Okay, so although the underlying wave that is being perturbed is a long wave, the perturbations with respect to which it is unstable in the Euler-Water wave context are not themselves long wave. So they do not fit within the KdV regime. Okay. All right. So let me now talk about a little bit more detail about a specific asymptotic model. I've already mentioned the NLS equation, and the rest of the talk will be specifically about the orbital stability of the elliptic solutions of the NLS equation. So again, this describes waves in deep water. It has a variety of periodic solutions, all of which, well, when I say periodic solutions, I mean that the modulus of the solution is periodic. Okay, there might be solution parameters where the solution as a whole is periodic, but typically the solution will be quasi-periodic, but the modulus will be periodic, as you'll see in a second. So right here, I have just an amplitude phase decomposition. I do not impose that the spatial part of my solution is real. So I'm allowed to have this phase contribution right here. And what I mean by, so the solution that I'm looking at are solutions where R of X is periodic. And only if e to the I theta of X, is typically going to have a different period. And I need some extra commensurability conditions for this combination to be periodic, but we won't need that in our stability analysis. So for us, it will suffice if just R of X is periodic. It's not too important to look at the specifics of what these solutions look like. More interesting, they can all be described in terms of elliptic functions. More interesting is this. So we have up to trivial lead symmetries like a phase shift and a translation. We have a two-dimensional parameter space for our stationary solutions, colored in purple here. So I have my parameters are the elliptic modulus going from 0 to 1 here on the horizontal axis. And then this offset parameter B, I'm referring to B as an offset parameter because the modulus of my solution squared is given by B plus something that looks a lot like sine squared, okay, an elliptic sine function. So B just raises the average value of the solution. So in order to have, of course, my solution form is this, and you can show that gets me all of the stationary periodic solutions. So in order for this R squared to be positive, and in order for, so K going from 0 to 1 is the restriction I get because I'm dealing with the elliptic functions. And then the constraint that R squared has to be positive restrict the B from 0 to 1. And similarly, I get that I need to be above this parabola B equals K squared because I have this C squared parameter, which comes in with my phase profile that needs to be positive as well. So I need to be in this purple region to have a valid solution of my problem. There's a lot of interesting limit cases here. If you are on the left boundary here, then you have a constant amplitude solution. And that is often referred to in the context of NLS as a Stokes wave solution. And everything that's going to follow, I'm not going to spend too much time on that, but everything that's going to follow in that context would really be about, really be about constant coefficient problems, and there's really very easy to do. Then I have over here in the corner, I have the Solomon solution of the focusing analysis equation. That is the only solution that is in my parameter space here that I will not consider because my analysis works for periodic solutions. Okay. Then we have at the top and at the parabola, I have what are known as trivial phase solutions, and there is not an extensive literature on stability of these solutions in the context of NLS, but the literature that there is typically deals with just solutions on the boundary of this domain. Again, this is a constant coefficient problem, that's straightforward. But then these solutions, you don't have this e to the I theta of x, you don't have a phase profile, and then it makes everything significantly easier. So what I want to discuss is what can I say about the stability of the solutions in this peripheral region. Okay, I don't want to just look at the boundary, I'm going to look at all of the solutions in the peripheral region. I'm going to skip a lot of detail, but following earlier work, kind of along the lines of what we did with KDV, result that I told you about, and then we followed that up with work on defocusing NLS. The problem is an inevitable problem. It's got a lax pair, got a number of conserved quantities. We use that whole machinery, put it to very good use, and we can establish a clear link between the stability spectrum of the linearization of your problem and the spectrum that you have for the lax pair. Okay. Again, I'm going to skip those details, but there is that connection. It comes through what is known as the squared eigenfunctions. That allows us to really get a complete understanding of the spectral problem of the linearization around the wave that you're interested in. And then we can step it up. If we find spectral stability results, we can get linear stability results using the SES lemma by Haragis and Papichula. Just to get an idea of the different kind of spectra that you can get. As I said, we have a completely analytical description of these spectra. These figures are produced by just a root finder on the one analytical condition that we have that describes the spectrum. Okay. So one thing to take away from this figure is that there's not a single spectrum that you're looking at here that is confined to the imaginary axis. All of these spectra go into the right half plane, which means they also go into the left half plane because of Hamiltonian symmetry, of course. But because they're all entering into the right half plane, the conclusion is that all of these waveforms are unstable. So that's disappointing. But maybe we can say more if we can restrict our class of perturbations a little bit. And that's what we'll do in the rest of this talk. So I'm going to look at, once again, subharmonic perturbations. I briefly mentioned what they are, but if we have a function that has period t, we say that g is subharmonic with respect to that function if g itself has period n times t, where n is an integer. Okay, so we're looking coperiodic would be subharmonic with n equals 1, same period, but we're also interested in n equals 2, n equals 3, and so on, subharmonic perturbations. So our spectral problem has periodic coefficients, and then from Fouquet or Bloch, we know that all eigenfunctions must be of this form, so it brings in the Fouquet exponent. And so by looking at a specific Fouquet exponent, we can look at specific classes of subharmonic perturbations. So here's again that same parabolic region, but now I've drawn some different curves in here. So using that characterization in terms of the Fouquet exponent, what you have here are these different blue-colored regions getting darker as you approach the origin. Yeah, so I guess I should explain what these numbers mean. First off, these curves that I've drawn into the parabolic region, they don't all go to the corner. You might think that they do, they all end somewhere on the parabolic region. So the endpoint of the first one is around here, the endpoint of the next one is around here, and so on. Similarly, on the left, the endpoints are at actually 1 over n squared. Okay, so 1 over a quarter here, 1 over a ninth here, and so on. So why are these regions important? Well, Gallet and Haragas already proved that everything in this parabolic region, in the whole parameter space, everything in the whole parameter space is orbitally stable with respect to coperiodic perturbations. When I say coperiodic perturbations in this analysis context, I mean periodic with the same period as the modulus of the solution, okay, as the envelope of the solution. So this one means that everything in this light blue region and below is stable with respect to periodic coperiodic perturbations or subharmonic perturbations of 1 times the period. Okay, so same period as the wave. Okay, but then there is this darker blue region where I have a 2, and what that means is that if I cross this curve, then now I lose stability. Sorry, I gain stability with respect to coperiodic perturbations. With respect to subharmonic perturbations of twice the period. If I go beyond this next curve, if I go into this region labeled 3, I've now gained stability with respect to subharmonic perturbations of 3 times the period, and so on. Okay, this nesting of 1, 2, 3, all being subregions of 3 is a subset of 2, 2 is a subset of 1. That's not obvious, and that's actually very specific to the nonlinear Schrödinger equation. Of course, 2 should be a subset of 1 because 1 divides 2. And of course, 4 should be a subset of 2. But it's not clear that 3 should be a subset of 2, right? Because now, because 2 does not divide 3, and so there are, subharmonic perturbations of 3 times the period that are not periodic for 4 times the period. Okay, so the nesting that we have here turns out to be this case for nonlinear Schrödinger. But if you repeat the same problem for, if you look at the same problem for the Sine-Gordon equation, you get something that's much more like a, what is that ordering again? Well, you get an ordering that's basically, 1 contains 2, 2 contains 4, and so on, but then 3 is not contained in those, and you get something that it's maybe more natural. But NLS has this nice structure, so we'll take it. So what's really going on as you cross one of these curves? So if you restrict yourself to subharmonic perturbations with a certain period, then instead of having these continuous curves being through the spectrum that we've been drawing, for a fixed n for a fixed for k exponent, you get a point spectrum. You get a subset of points on these curves, and as long as that subset is confined to the imaginary axis, you will have stability with respect to those perturbations. So, for instance, right here, I start with a solution that's slightly below the curve dividing the n equals 1 and the n equals 2 regions, and so it is in the n equals 2 region. It is in the 2 region, meaning that the in the stability spectrum, I have eigenvalues that are on the imaginary axis. As I push the solution parameters so that the solution goes on the curve, what I have is a Krein collision of 2 eigenvalues actually with opposite signature, as you can see here. I have a Krein collision happening right at the top of the figure 8. And then if I go into the n equals 1 region, as I said earlier, I lose stability with respect to subharmonic with n equals 2 perturbations, and that's manifested by these eigenvalues coming off as a result of the Krein collision. Okay, the same thing happens as you cross each one of these curves. Okay, so how do you go about, so now I have spectral stability and even linear stability with respect to these restricted classes of subharmonic perturbations in different regions. How could I go about using that to prove orbital stability? So I'll give you a little outline of how that works. So what I want to know is that all solutions that are spectrally stable, I'd like to show that they're also orbitally stable. And so we've now managed to do that. We will first establish formal stability, so we're going to find the Lyapunov functional, and then we can rely on the results of Berlacher, Chatin, and Strauss, or Maddox and Sachs, to establish orbital stability. Okay. As I already mentioned, for n equals 1, so for the coperiodic or harmonic perturbation, Gallet and Haragas proved orbital stability, and they showed that the Hamiltonian of the problem is a Lyapunov functional. Okay, but that's of course for n equals 1. In other words, 1 period, right? Periodic perturbation of the same period as the solution. So a quick definition: if I look at the quadratic part of the Hamiltonian, then that's known as the Krein signature, and I've used some notation here. So this is L is the hashing of my problem. That's just a linearization around my stationary solution. Okay. Now I'm interested in taking this inner product over capital N periods because I want to look at subharmonic perturbations. For n equals 1, you get the periodic case. Now, because we've used these methods from integrability, we are actually able to calculate. We have the eigenfunctions for the spectral stability problem in hand. And the different directions in our space are just parameterized by different lax parameters. And if I'm going to fix the subharmonic perturbations, then the set of all these lax parameter values that I'm interested in is a countable set. As I mentioned, for n equals 1, there's no negative direction, and this the energy functional is the Lyapunov functional for the coperiodic perturbations, and this is really what Gallet and Haragas used. But if you increase n, if you allow for true subharmonic perturbations, that's no longer true. Now there are negative directions that appear, and we need something else to establish orbital stability. Okay. So of course we have a lot of choice because the nonlinear Schrödinger equation is a member of an infinite hierarchy of inequal problems with commuting dynamics, and so now I have an infinite number of conserved quantities. I will, typically we denote them as Hn. The capital N again refers to the number of periods I'm integrating over. And I will actually construct these hat of conserved quantities, which are a linear combination of the nth conserved quantity and all the lower order ones. That brings in these superposition coefficients C and J that I will get to choose at my convenience. So obviously, if the H's are conserved quantities, then H hat is a conserved quantity as well. Okay, so the question is, can we find these coefficients C and J? Can we choose those coefficients so that the H hat is a Lyapunov functional for the T2 dynamics or for the for the T dynamics? That's the really problem we're interested in. So the first thing we're going to do is we're going to impose that, of course, we have a stationary point, and that imposes some constraints on the C and J's. And then the crucial observation is that the Krein signature that we get from integrating over capital N periods of the nth conserved quantity is simply, so that's the definition right there, turns out to be related to the Krein signature related to the Hamiltonian. Okay, so going back to, so here's the Hamiltonian, its quadratic part, basically these terms, and then whatever you get from linearizing around the wave from this term. The Krein signature associated with this conserved quantity is related to the conserved is related to the Krein signature related to the nth conserved quantity by simply multiplying by a polynomial that is only dependent on the lax parameter and the coefficients that I've used for my superposition, the construction of these hatted conserved quantities, these H hats. And so now we know that this changes sign if I let n be greater than 1, right? There's a number of sign switches. And so the goal is do we have enough freedom in this choice of this polynomial to wherever this switch is signed, to have this switch signed as well, so that overall my Klein signature associated with H hat would be a sign definite quantity. Okay, so and it turns out you have exactly the right number of constants to work with, and so you can establish that this Klein signature is always positive, allowing you to establish that you do indeed have a that H hat with those constraints is indeed a Lyapunov functional, and that establishes then formal stability, and then it's just a straightforward application of Graka-Strauss to show that we actually also have orbital stability. So let me summarize. The stability of the periodic travel waves within the context of the full water wave problem is very poorly understood. We're getting better. So we have a new understanding about the measurement of free instability going back to this year. I believe that tomorrow we'll hear a talk by Vera Her, where she will also tell us that there is improved understanding of the high frequency instability, and we're also working in that direction. And then, another lesson is that we can gain some intuition about these stability results in the context of the full problem from the asymptotic models. That seems to work well in deep water, but it definitely, and for the measurement of free instability, but it definitely doesn't work so well in shallow water, where KV tells us everything is stable with the perturbations, of course, that fit its regime. And that's all I have. Thank you very much.